Bismillahirrahmanirrahim. Hello dear students, I hope you are all fine. I welcome you all to the class of real analysis by Walter Rudin. Our discussion is continuing on chapter number 3, numerical sequences and series. In today's lecture we will discuss a very important theorem, Bolzano-Weierstrass theorem for K tuple. In elementary real analysis you have already known Bolzano-Weierstrass theorem for real set of real number R. But in this video we will discuss its proof for RK, k-dimensional space. This theorem can be stated as proof that every bounded sequence in RK contains a convergent subsequence. So this is the statement of Bolzano-Weierstrass theorem for RK. RK means a k-dimensional real space. Firstly, I will elaborate this theorem by a simple example. Consider a sequence xn in R square. R square means a two-dimensional real space having two coordinates. So my sequence xn has the two coordinates minus 1 raised to power r 1 over n. So this is my sequence in R square. So the sequence consists of points in the plane. Here you can notice that each coordinate is itself a sequence in R. Minus 1 raised to power n, this is itself a sequence. 1 over n, this is also a sequence in R. For your convenience, I am constructing following table that shows a few points, or you can say the terms of the sequence. When you put n is equal to 1, this becomes minus 1 raised to power 1. This is minus 1. 1 over 1, this is 1. So this is the first term of the sequence. When you put n is equal to 2, this is 1 minus 1 square. This is plus 1. And when you put n is equal to 2 here, this becomes 1 over 2. So at n is equal to 3, this is minus 1 over 3. At 4, this is 1 by 4. At 5, this is minus 1 over 5. Here the first coordinate of the sequence, that is minus 1 raised to power n, always lies between two values minus 1 and plus 1. When your n is an even integer, this will be plus 1, and for odd integer this is minus 1. And the second coordinate, you can notice that this always lies between 0 and 1. At n is equal to 1, this is 1, so that's why I am taking here less than or equal sign. But 0 is its limit, but it can never close to 0, can never equal to 0, so that's why I am not taking here equal sign. Thus the sequence still lies inside the rectangle formed by the closed interval minus 1 to plus 1 and 0 to 1. So this is the range of our sequence. This set represents the range of our sequence minus 1 raised to power n and 1 over n. And you know rectangle is always bounded in R square. So I can say this sequence is a bounded sequence in R square. Next I will show, I will take one or two subsequence of this sequence, and we will observe that subsequences are convergent subsequences. Now consider the subsequence. I am denoted x by x and k, whose first coordinate is 1 and the second coordinate is 1 over 2n. You know 1 over 2n is a subsequence of 1 over n. In 1 over n, the denominator is n, while in this sequence my denominator is always an even integer. So this sequence 1 over 2n is subsequence of 1 over n, while the first coordinate is the subsequence of minus 1 raised to power n, because for all integers minus 1 raised to power n is either plus 1 or minus 1. It has only two outputs, so I am considering plus 1. So this is a subsequence in R square of xn. Now you can notice that the first coordinate, that is 1, This is a constant sequence, and constant sequence is always approaches to that number. So 1 approaches to 1. The second coordinate is 1 over 2n. So when you take n approaches to infinity, this sequence approaches to 0. So your subsequence 1 comma 1 by 2n approaches to 1 0. It means this subsequence has a unique limit 1 comma 0. Similarly, if you consider a second subsequence denoted by y and k, whose first coordinate is -1 and the second coordinate is given by 1 over 2 and -1. Now my denominator is an odd integer. Again, you can notice that when you take n approach to infinity here, this becomes 1 over infinity and 1 over infinity is 0. So -1. So the limit of this sequence is -1 comma 0. Hence the bounded sequence. Hence our bounded sequence xn. And further you can notice that this is an interesting thing. This is bounded sequence, but it is itself a divergent sequence. Why this is a divergent sequence? Because the first coordinate is not a convergent sequence, because it has two limits, either -1 or +1. So that's why the final sequence xn is not a convergent sequence. Anyhow, we have only need that it should be a bounded sequence. So hence the bounded sequence has two convergent subsequences. So I hope by using this example you have now idea of this theorem. Now next I will prove this theorem in general. Let xn be a bounded sequence in Rk, the kth dimensional real space, where xn in a vector or a coordinate form is clearly xn is a bounded sequence in Rk. So that's why xn has a k tuple, or k, you can say it has a k coordinates. The first coordinate is denoted by xn 1, xn 2, xn k, where each coordinate xn1, xn2 up to so on xnk is a sequence in R, and you can see this from above example, in which I said that each coordinate, this is -1 raised to power n and 1 over n, both of the coordinates are itself sequences in R. So by the similar fashion here, each coordinate of this sequence is itself a sequence in R, denoted by these notations. Since it is given that the sequence xn, this sequence, final sequence, this sequence xn is a bounded, so by the definition of bounded sequence, there exists a positive real number m such that the norm of this sequence is always less than or equal to m. These two lines are generally called norm or magnitude of this sequence. This should be less than or equal to that positive real number m for all n belong to n. So when you say our original sequence, which has a k coordinates, is bounded, this implies each coordinate sequence is bounded. It means each term of this sequence, each coordinate of this sequence individually is also bounded. So each sequence is bounded by this number m. So xn I is less than or equal to m, where I start from 1 to end at k. Next, we will apply Bolzano-Weierstrass theorem in R. What is Bolzano-Weierstrass theorem in R? This theorem says every bounded sequence of real numbers has a convergent subsequence. As xn1, xn2, these are all bounded sequences. So by Bolzano-Weierstrass theorem in R, these all sequences have a convergent subsequences. Just a minute, please. Okay. Apply this theorem to the first coordinate sequence xn1. There exists a subsequence. I am denoting it by xn1 by this notation, such that this subsequence is a convergent subsequence. So it must have a limit So say this converges to A1. Similarly, consider the second coordinate sequence xn2. It is also bounded, so it has a convergent subsequence xn2, and such that its limit is a2. Continuing this process for all coordinate sequences, we can find a limit vector denoted by a, which has a k coordinates as a1, a2 up to some ak, such that a1 the first this is the first limit of your first subsequence, a2 is the limit of second subsequences, ak is the limit of the kth subsequences. Since every coordinate converges, so the subsequences, final subsequence yn, which is denoted by xn1, xn2 up to some xnk. This complete sequence, this is the subsequence denoted by yn. This converges to a1 because xn1 converges to a1, xn2 converges to a2, xnk converges to ak. So finally, this coordinate sequence subsequence converges to this vector, and it is denoted by a. And this shows that your subsequence yn converges to some real number a, uh, some number in rk. So this shows yn belong to rk, converges to a. That is our target. So I hope now you have a clear understanding about today's theorem. If you find this video helpful, kindly like, share and subscribe my channel. See you in the next lecture. Take care. Allah Hafiz.